Hello everyone, this is Chandan and you are watching the learning field. Okay, so we are continuing the numerical analysis lecture series. This is the lecture 5 of numerical analysis, and this lecture is also based on interpolation. Okay, in the last lecture we discussed the Lagrange interpolation. Okay, Lagrange's interpolation, and in this session we are going to discuss the Newton forward and backward interpolation, some properties, the examples, and some results regarding these two, Newton forward and Newton backward interpolation. Okay, and so let's start. And before starting, I am requesting you to all those who are new in my channel, please like the video, comment if you have any doubt in the comment section below, and don't forget to subscribe the channel. Okay, and one more request is that we are very close to 1k subscribers, so please like, comment and share with your friends to grow more, to grow fast. Okay, so this is my request. So now we're starting with what? First, in this video or in this session we are going to discuss what? Newton forward and Newton backward interpolation. Okay, now when we use forward interpolation and when we use backward interpolation, okay, see, if some data sheet is given, suppose xi's values are given and f of xi at the point are given. Okay, suppose this is x0, x1 and so on xn, suppose. Okay, and the values are given at fx0, f of x1, or you can say this is equal to yi, and f of x1 and so on f of xn. Okay, suppose we have to find the value, any one of the value in between. Suppose the value lies between the starting at the tables. Okay, suppose this value is 1, this value is 5, and we have to find the value at the 5 at the point x equal to 2 or 3 or 4. Okay, this type of points, and also point 2.5, 3.5, this type of all the points in between 1 and 5, or you can say 5 and then suppose this is 6, or this value. If we find any value in between the 5 and 6, that is the node or the point xi, if the value which we have to find lies in the starting of the tables, that is the starting side of the table. Okay, then we use what? Forward interpolation. Okay, and if the points which we have to interpolate or which we have to find the values of fxi during or using the interpolation, suppose this value lies between this end side of the or back side of the table. Okay, then we use the backward interpolation. That's why the two names of these interpolations are forward interpolation and backward interpolation. Okay, now before going to the forward and backward interpolation, we discuss one very important topic, which is differences. Okay, so which is finite differences. Finite difference. Okay, and here finite difference means one is forward difference and second one is backward difference. Okay, so the first here, the first forward difference, first forward difference of any function, just a second, of any function fx, suppose. Okay, is denoted by what? Is denoted by delta of fx. Okay, this delta fx, this is equal to f of x plus h minus f of x. Okay, so this is the first forward differences, where what is this h? Suppose xi is and suppose there are n plus 1 points of interpolation, suppose x0, x1 to xn. Okay, these are the points given. Okay, and value at these points of the function is given. Okay, and suppose xi is equal to x0 plus I into h. And one more thing is that here it is very important that these interpolations okay, interpolation with equal interval, that means length of this x0 and x1 and x1 and x2 are same. That is, we discuss here two types of interpolation which we already discussed. One is equal interval, equal subinterval, and second one is or equal number of nodes. gap in between any two nodes are equal, and second one is unequal. Okay, unequal. And in unequal we already discussed the Lagrange interpolation. That's why the theorem, one theorem is there. Suppose the theorem is such that what the Lagrange interpolation exists and unique. That means in case of unequal subinterval or in case of equal length of subinterval, okay, in both the cases Lagrange interpolation exists and unique. Okay, and in the equal subinterval or equal what unequal interval or equal interval, equal interval, here in this case we discuss the Newton forward and backward interpolation. Okay, that's why xi equal to, we can write x0 plus iota into h. Okay, so this is the first difference, delta of fx. Okay, we can write again here delta of f x0, this is equal to what, f of x0 plus h minus f of x0. This is also can be written as f of x1 minus f of x0. Okay, so this is the first forward difference. So that is why we can write delta of y0, y0 means fx0, this is equal to y1 minus y0. Okay, so this is the first differences, finite differences. That is you can also write delta of y1, this is equal to y2 minus y1, delta of y2, this is equal to y3 minus y of 2. Okay, this type of results, or this type this is the definition of the finite forward differences. Okay, now if we write the second order finite difference, then the second order finite difference we can write is as such as delta square of y. Okay, delta square of y0, you can say this is equal to, we write delta of delta y0. Okay, so delta of delta y0 means delta of delta y0 means what, y1 minus y0. Okay, y1 minus y0, that means here delta of y0 delta of y1 plus delta minus, this is minus delta of y1 minus delta of y0. Okay, so delta of y1 equal to, we already know that this is equal to y2 minus y1, and delta of y0 means minus of y1 minus y of 0, this one. Okay, so this is equal to y2 minus 2y1 plus y0. So this is the second order finite difference. Similarly, we can calculate the third order, fourth order and fifth order and up to kth order finite differences. Okay, in general we can write what we we can write delta kth order finite difference, delta k of y0, if we write with respect to this point y0, then this is equal to yk minus yk minus kc1 yk minus 1 plus kc2 yk minus 2 minus that is alternate plus minus 1 to the power k into y0. So this is the general expression for the kth order finite differences. Okay, forward finite differences. Okay, now here we write the finite forward finite difference table. Okay, how can we calculate, or this table is very important to calculate the values or to formulate the values of the given data sheet, or to calculate the given interpolation point. Okay, interpolation. So this table like that. Okay, I just write the format of the table. This is x, this is y, then this is delta y, this is equal delta square y, delta cube y, and suppose delta power 4 y, this type of table. Okay, so here the values of x0 x1 x0 x1 x1, okay, x2 x3 and so on. Suppose we take here up to x4. Okay, and this is the given values y0 y1 y2 y3 y4. Delta y, this is equal to delta of y0, that is this is equal to y1 minus y0. okay, delta y0, we write delta y0 in between this, okay, in this position, okay, delta y0, then delta y1, then delta y2, then delta y3, and then in between this delta square y0, delta square y1, delta square y2, okay, and then delta cube y0 and delta cube y1, and here delta to the power 4 into y0, we write this one, okay. So this is the finite forward difference table, okay, finite forward difference table, okay. Okay, now we then go to the backward differences, define the backward differences, okay. Backward differences. Now the backward difference is defined by any function delta fx, this is equal to f of x minus f of x minus h, okay. This is the definition, or we can define the backward differences as in the terms of this fx and f of x minus h, where xi is equal to x0 plus iota h, I equal to 0 1 2 n, if there are n plus 1 distinct nodes or distinct point, okay, which are equally spaced, you can say. So delta fx is equal to this one, therefore delta of f of x1, this is equal to f of x1 minus f of x0, this is equal to y1 minus y0, okay. Similarly we can write delta of f of x2, this is equal to f of x2 minus f of x1, this is equal to what, y2 minus y1. We can write this in this way, okay, that is delta of yn, this is equal to y, we can write this is equal to yn minus yn minus 1, okay. So this is the first order backward difference. Now the second order backward difference, delta square y, suppose delta square y, here we write any of the, suppose delta square y2, it is starts with first term 2, this is equal to delta of delta y2, okay. So this is equal to delta of delta y2 means y2 minus y of 1, okay. So this implies delta y2 minus delta of y1, so this is equal to y2 minus y1 minus y1 minus y of 0, okay. So this is equal to y2 minus 2y1 plus y0, okay. So this is the first backward differences, because if we write deltas, we can't write the second order differences of y0 or y1, okay. And delta cube y equal to delta square y2, we can also calculate delta square y3 equal to something, okay. You can calculate in this way, okay. In general we can write, suppose delta power k, the kth order backward finite differences of I, this is equal to yi minus kc1 y I minus 1 plus kc2 what y I minus 2 minus 1 to the power k into y I minus k, okay. This is the general expression of the backward differences of any point, okay, or any node, you can say, okay. Now going to the Newton forward difference interpolation formula. We here just write the formulas, because if we want to complete or complete procedure to make the formula, then it will be very big session, okay, very lengthy session, so I avoid this, okay. So Newton forward difference formula, okay, Newton forward difference formula. What is the formula? Suppose y equal to fx be the function y equal to fx with a function whose explicit form is unknown, that is the analytical formula is unknown. The points are x0, x1 up to xn. Okay, and xi equal to x0 plus iota into h, I equal to 0, 1 to n. Okay, that is h is the spaced, okay, distance, where h is the spacing, you can say. So if it is required to construct a polynomial phi x of degree lesser or equal to n, so we construct a polynomial phi x which is the degree of the polynomial is less equal to n and satisfying the conditions what yi equal to phi of xi, okay, for I equal to 0, 1 to n. Okay, this is the condition, and we know the what is the expression, general expression for phi. We write this in case of Lagrange interpolation formula, this is equal to a0 plus a1 into x minus x0 plus a2 into x minus x0 into x minus x1 and so on. Okay, we can take this form of phi x. Okay, so now our work is what, we have to calculate these coefficients a1, a0, a1, a2 and an. Okay, so after calculation I just skip this, I just write the, okay, I just write the formula here. Okay, so the Newton interpolation formula, forward interpolation formula phi x, this is equal to what, y0 plus u delta y0 plus u into u minus 1 by 2 factorial delta square y0 plus u into u minus 1 into u minus 2 by 3 factorial into delta cube y0, okay, delta cube y0 plus so on, plus the last term is u into u minus 1 into u minus 2 into u minus n minus 1, this is in bracket, by n factorial into delta n nth order finite difference of this term. Okay, where this u equal to what, this u equal to x minus x0 by h. Okay, okay, we all know that the where x I equal to what, xi equal to x0 plus iota h. Okay, so this is the Newton forward interpolation formula. Okay, we will take the example of this and we solve one problem regarding this Newton formula. Okay, so this is the Newton, or this is also known as Newton-Gregory. Okay, Newton-Gregory forward difference interpolation formula. Okay, now if we take an example, now if we take an example of this formula, suppose let us take let us take the example as example. The following table gives the values of exponential x, certain equidistant values of, find the values of x. So we have to find fx equal to given, or this is equal to y, this is equal to exponential x when x equal to 0.612. Okay, using Newton forward difference interpolation formula. Newton forward. Okay, and the given table is, given table or data sheet is x and y. X and y are 0.61, 0.62, 0.63, 0.64, 0.65. The values are 1.840431, 1.858928, 1.877610, 1.896481, 1.9155, 1. Okay, so this is the given table, and from this given data we have to find the value of 0.612. See, this point 0.612 is position of this point is where? In this here, okay, in between 0.62 and 0.63. That means this point where situated at the forward part of the table. Okay, that's why here we use the Newton forward interpolation formula. Okay, now we have to find the difference table first. We have to write the difference tables first. Difference table. Okay, so the difference table, this is equal to, this is x, this is y, this is then x y, then delta y, delta square y, and we write as our need, okay, of the delta, remaining delta. Okay, and we continue the table, or we continue the calculations up to when? Up to this delta square or this forward difference is coming a constant. Okay, after up to when the finite difference coming a constant, we calculate up to that finite differences, up to the order of the finite difference, or order of the difference. Okay, so this is here, this is equal to 0.61, 0.62, 0.63, 0.64 and 0.65. okay, now the values are 1.8404, 1.840431, 1.858928, 1.877610, and 1.896481, 1.915541. okay, so now we find the differences of delta y. Delta y means first we subtract this one to this one and write this position is delta y0 position. If we subtract this y1 minus y0, we get the first point delta y0. okay, so this is equal to 0. This subtract of this, okay, this minus this, 0.018497. then the second difference is 0.18 0.018 682. The next difference is 0.0188 and 71. okay, next one is 0.019060. okay, now the second difference we write this one minus this one, this one minus this one, and this one minus this one. okay, so the difference is 0.000, okay, 185. Here we take the 6 digit after decimal, because this is a standard calculation. In case of interpolation, we have to find the interpolation formula when we have to find, or we have to correct up to 6 digit, then we work with 8 digit after decimal. okay, this is a general rule in the practical of any interpolation classes. If we need to calculate, or if we correct up to 8 digit, then we need to take the 10 digit after decimal to correct this. okay, so this is a general rule, and since this is a simple formula, so we take here the 6 digit, okay, after decimal. Now 0. What next one is 0.00189, and then this is 0.000189. see here, these two are constant already given, comes. okay, so this is 0, and this one is what? 0.0000 and 4. This is also constant, almost constant, up to 4 decimal places. okay, so we stop here the calculation of the table at the order of delta cube. okay, so now we calculate what we needed. First we need what? The value of x0. In the formula, x0 equal to what? 0.61. okay, then we have to find the x equal to what? The we have to find the value of 0.61. 2. Okay, h equal to what? H equal to, you can write any of the differences, 0.62 minus 0.61, this is equal to 0.01, h equal to, okay, u equal to what? U equal to x minus x0 by h equal to 0.612 minus 0.61 by h means 0.01, okay, this is equal to 0.2 here. So these are the quantities needed in the formula. Okay, so now we write the formula here. The formula is, we have to find y of x or phi x, we just write here. So phi x or y at the point what? At the point 0.612, this is equal to y0 plus u into delta y0 plus u into u minus 1 by 2 factorial delta square y0, sorry, y0 plus what? U into u minus 1 into u minus 2 by 3 factorial delta cube y0. Again, the remaining terms are 0 because the remaining delta order of the deltas are not present in the given table. Okay, so that means what? See, one thing here is that what? Delta y0, delta square y0 and delta q y0, which quantities? So delta y0 means this quantity, just a sec. So delta y0 means, see, this quantity, okay, delta square y0 means this quantity, and delta q y0 means this quantity. That means, see, this type of values you can take here. And I also here said that in case of backward interpolation, the values will take in from this side. Okay, we just comes to that topic in the backward interpolation. Okay, so this is equal to the value of u equal to what? The value of u equal to 0.2. Okay, h equal to 0.01. So y0 means what? Y0 means the value given here. This one is the value of y0, 1 point. So this is equal to 1.840431, this one, plus the value of u is equal to 0.2 and delta y0 means the value we get 0.018497 into 0.018497 by this is equal to this one. Okay, and then we get u into u minus 1, that is 0.2 into 0.2, oh sorry, 0.2 minus 1, u into u minus 1 by 2 factorial, that is 2 into the delta square y0 means this term, delta square y0 means this term. So this one 0.000185 into 0.000185, okay, plus 0. U into u minus 1 into u minus 2 by 3 factorial means 6 into the value of delta cube y0 is 0.000004. I think here I made a mistake. Here again another 0 will be here, 5, 0 and 4. Okay, so this is our calculation, and if we calculate this, then we get the answer 1.844115. Okay, you can calculate this calculation. Okay, so this is the answer and this is the example. Okay, so see, understand this example. We need to find the value in between which is present in between this. Okay, that's why we use here the Newton forward interpolation. In case one data value or data table is given and you have to find the value of something, but you don't give or you don't know that or you don't mention in the exam that which method you can use. So this is the method you can use if the value of the point is in the forward of the table, in this table, then we use the forward interpolation, and if the value is present in the back side, then we use backward interpolation. Okay, and one more thing here is that if the value is present here, suppose we have to calculate the value 0.625 something, okay, then which values are changed in our calculation? See, this is very important. Okay, So if we calculate this term, then y0 value is this one. Okay, we take y0 equal to this, so y0 equal to then this we take delta square y, delta y1, delta square y1, and this term. Okay, so these three terms are then taken diagonally, you can see from the table. Okay, so this is the another important note which I already said here. Okay, now what is the error in Newton forward interpolation? Okay, so this is also very important, error in Newton forward interpolation or formula. So Ex, this is equal to x minus x0 into x minus x1 into x minus xn into f of n plus 1 xi by n plus 1 factorial. Okay, so this is equal to what? This is equal to, so if we divide these terms by h, then what we get? X minus x0 by h. What number of h? H equal n plus 1 number of h we get here. Okay, since we convert this term in terms of u, since u equal to x minus x0 by h. Okay, since there is n plus 1th term, therefore x minus x0 by h, if we write x minus x0 by h into x minus x1 by h dot x minus xn by h, okay, into f of n plus 1 xi by n plus 1 factorial. Okay, so this is equal to, we can write u into u minus 1, this term is u, this is u minus 1, and so on, and u minus n into here we write h to the power n plus 1 into h to the power n plus 1 f n plus 1 xi by n plus 1 factorial. Okay, this one, where xi is what? Xi is lies between, we already discussed this term, it lies between what? Minimum of x0, x1, xn and maximum of x0, x1, xn. Okay, also you can write f of n plus 1 into xi, this is nearly equal to h power n plus 1 into delta n plus 1 y0. Okay, so the error E, this is equal to, finally we can write u into u minus 1 error formula into u minus n by n plus 1 factorial into delta n plus 1 y0. Okay, so this is the error formula of the Newton forward interpolation. Okay, this is the error formula of Newton forward interpolation. Now we discuss the Newton backward interpolation. Okay, Newton backward interpolation. Okay, there is the also same case where the phi x equal to this, we just write in the forward interpolation formula case. Okay, so this one is the phi x, here same phi x we just write. Okay, same phi x and just the formula from the back side. Okay, we here write just the formulas. Okay, so the formula, that is the Newton interpolation formula, phi x or any, this is equal to yn, and in the back forward interpolation this is y0 plus x minus xn just a minute, sorry, this is not the complete formula. So this is equal to what, yn plus v h into delta yn by h plus vh into v plus 1 delta square yn by 2 factorial into h square plus h into v plus 1 into, here these are terms are u into u minus 1 terms in the forward formula, and in the backward formula these are plus terms. Okay, h plus 2, sorry, this is h into v, 3h will be here. Okay, I just write the wrong side. This is equal to v into h, v plus 1 into h, here the h terms we write, and v plus 2 into h by 3 factorial into h cube. Just a minute, sorry, here I made some mistakes. Phi x, this is equal to what, yn plus v yn plus v into v plus 1 by 2 factorial the square yn plus v into v plus 1 into v plus 2 by 3 factorial into delta cube yn plus so on, plus the last term is v into v plus 1 into v plus 2 into v plus n minus 1 by n factorial into delta power n yn. Okay, so this is the Newton backward interpolation formula. Okay, where v equal to what, v equal to x minus xn by h. Okay, where x I equal to what, x0 plus iota into h. H is the spacing, we can say. Now we take an example here. Okay, we take an example. Here we take the example, but suppose the table value of the table is example x and fx. Okay, so suppose 0.20, 1.6596, 0.22, therefore h equal to what, h equal to 0.02 here. Okay, 1.6698, 0.24, 1.6804, 0.26, which is equal to 1.6912, 0.28, 1.7024 and 0.30. This is equal to 1.7139, this one. Now we write first the difference table. Okay, x fx, delta fx, this one. Okay, so 0.20, 0.22, 0.2624, 0.2826, sorry, 0.26, 0.28 and 0.30. So fx equal to what? 1.6596, 1.6698, 1.6804, 1.6912, 1.7024 and 1.7139, this one. So delta fx means this minus this, then this minus this, delta square y0, y1, y2 and y4. Okay, this is equal to 0.0102, 0.0106, 0.0108, 0.0112 and 0.0115. Okay, this one. And delta square fx equal to what? Delta square fx, this is equal to this minus this, this minus this. So this is equal to 0.0004, 0.0002, 0.0004, 0.0003. Okay, then the delta qfx is minus 0.0002, 0.0002, then minus 0.0001, and then the next error is 0, you can say, or constant. So here xn equal to what? And sorry, we have to find the value of what? We have to find the value of f of, we have to find the value of f of 0.29. Okay, this is the finded value. This is equal to what? So here xn equal to what? So xn, we need xn here. Xn equal to what? We take 0.30, since the value 0.29 lies in between these two. Okay, so xn equal to 0.30 and x equal to what? X equal to 0.29. Okay, and h equal to, we already write 0.02, difference between xi's into xi and xi plus 1, and v equal to what? X minus xn by h, which is equal to 0.29 minus 0.30 by 0.02. This is equal to minus 0.5. Okay, so this one. Now we write the formula. So f of 0.29, this is equal to f of xn, that is yn, plus v into delta f of xn plus v into v plus 1 by 2 factorial delta f of delta square f of xn plus v into v plus 1 into v plus 2 by 3 factorial delta cube f of xn. Okay, plus the remaining terms are 0, that's why you skip the topic, the the remaining terms. So this is equal to 1.fxn value is what? 1.7139. So this is the fxn value, this is the xn value, fxn value, this is the xn value. Because the point lies in between here, therefore we take this line. Okay, this is the calculation line. Okay, so 1.7139 plus v means what? Minus 0.5. So we write minus 0.5 into delta f of xn means 0.0115. This one is the delta f xn, delta square f xn, delta cube f xn. Okay, so if we write this one plus minus 0.5 into minus 0.5 plus 1 by 2 factorial means 2 into delta square f xn means 0.0003, and then again plus term minus 0.5 into minus 0.5 plus 1 minus 0.5 plus 2 by 3 factorial means 6 into minus of 0.0001. So if we calculate, then we get 1.7081 7081 this term. Okay, you can calculate this, okay, and find this answer. Okay, so this is the example of Newton backward difference. Okay, now we write the error term of Newton backward difference. Okay, so error term is equal to what? E of x, this is equal to v into v plus 1 into v plus 2 plus v plus these are the product, v plus n h to the power n plus 1 f of n f power f n plus 1 xi by n plus 1 factorial. Okay, where b equal to, you all know that, x minus x n by h, and xi lies between minimum of x0 x1 to xn and maximum of x0 x1 to xn. Okay, so this is the error term of Newton backward interpolation. Okay, and we already discussed the example of this, and in a GATE syllabus only it says the Lagrange's interpolation and Newton's interpolation. Newton's mean Newton's backward plus forward plus backward. Okay, so I think we will study the Newton divided difference formula also. Okay, divided, we should need divided difference, because from divided difference question can be made, and also this is important for CSIR NET exam and any other higher math exams, divided difference also. Okay, so in the next class we discuss the Newton divided difference, and I think from Hermite interpolation there is question. Hermite interpolation, I so once the questions paper of GATE or NET, I think in CSIR there is a questions from Hermite interpolation. Therefore we also cover the Hermite interpolation also, because we always want to be on the safe side. Okay, so this is the class for today, and in this lecture we cover what? We cover the Newton forward interpolation and backward interpolation, and error terms of those interpolation formulas, and example of those interpolation formulas. Okay, so if you like this content, and if the content helps you will like little bit, then please give a like to this video, share it with your friends, and subscribe the channel. Thank you friends, see you again in the next video. Thank you.